Hey everyone. Today I'll be talking about the pretty much very simple story, how we run some large circuits at BlueQubit to do some useful things. And I'll be sharing the insights and findings that we had from these experiments. And when I say large circuits, I mean we had quantum circuits with thousands of gates, with the largest circuits getting to 18,000 gates on 72 qubits. And when I say useful things, I mean image processing. We've done some tasks with image classification that I'll be talking about. And yes, I'll be sharing some insights on our quantum runs on IBM and Quantinuum. The problem that we've looked at is simple image classification. And we worked with Honda for this problem. The data set is basically taken from this HSD data set, which stands for Honda Scene data set. It's a publicly accessible data set that Honda uses for their self-driving car projects. And the problem that we looked at basically is comprised of 2,500 images, and there are 4 classes that we'll be classifying against. You can see examples of those classes. Basically, we're looking at images and trying to determine whether or not it's what time of the day it is, day versus night, and what are the road conditions? Is it snowy or is it dry? So we have 4 classes like that. We also looked at classical approaches for this problem. We looked at fancy convolutional neural networks as a candidate for the best possible classical algorithm that we'll be benchmarking against. And also we looked at some baby neural networks, very kind of out of the box, no optimization. And the idea is that quantum algorithms today are, again, the first steps in this space. So it also makes sense to compare early stage quantum algorithms with early stage neural network algorithms. And also I'll be talking about the exact setup of the quantum classifiers that we used. So what we do on the quantum side, basically we take the image. First we take the grayscale version of the image, and then the solution is comprised of 2 parts: the block amplitude encoding and the actual classifier part. And you can kind of see a high-level diagram of that at the bottom of the slide. Block amplitude encoding is a fancy term for just chopping the image into different smaller pieces and doing approximate amplitude encoding to input that image data into your quantum circuit. That part is represented by the green area, block amplitude encoding, on the diagram. And after that, we basically have a variational ansatz that we train to train the classifier that we'll be using to classify this data set. And the rest of the setup is pretty similar to classical workflows. We split the data into train and test. We train on the training data, and then we report some metrics on the test data. So jumping ahead, the final results that we get from this kind of workflow, as I mentioned, we have the quantum runs, and then we have the fancy CNN model, and we also have the FCN model, which stands for fully connected network. This is the one where, again, we didn't do a lot of optimization with convolutional layers or other things. We just took a regular neural network, fully parameterized, and run the classification through it. And the results basically show that the quantum classifier can achieve similar results to the simple neural network with much fewer parameters. And it's falling behind the fancy neural network model, as you can see, that's using as many parameters. And this basically goes to show that, again, we're not only benchmarking our quantum algorithms with just brute force or simple classical approaches, but also we're going the extra mile of trying to find the best classical alternatives so we can compare our algorithm and actually make claims about how good it is. And here we see that, yeah, even though it's falling behind the best possible classical approach, it's still in the same ballpark. And now I'll talk more about the actual quantum runs. So these are not simulation, these are actual runs that we did on IBM and Quantinuum. So this particular image shows the results of just the data loader part of the earlier diagram I just showed, and the fidelity of our data loader module for different circuits that go from 250 2-qubit gates all the way to 2,000 2-qubit gates. This experiment was done on IBM Brisbane. The y-axis basically is a metric that shows how far from the true distribution we are. Lower numbers are better. 0 basically means we got the exact same distribution that we are going for. The red line here is the baseline. The red line is what you would get if you had a fully noisy state. And pretty much anything under the red line means you are getting signal. And we see that as expected, as we grow the number of 2-qubit gates, the results become more noisy, but even at 2,000 2-qubit gates, we still have significant signal. And all these experiments were done on 72 qubits, by the way. We do similar experiments on Quantinuum. The setup is a bit different. Here, instead of we have fewer circuit runs here. Also, we are looking at fewer observables. But again, the y-axis is the metric that we use to compare against the ideal simulation results. In particular, the blue bars here are the ideal simulators, and the other 3 bars are the 3 different circuits that we run on Quantinuum. In particular, this one is using the Quantinuum's H1 chip that has 20 qubits. And we are not using that many shots for this experiment, so there is also a lot of variance that can be attributed to the low number of shots, so that also needs to be taken into account. But overall, you can see that, again, there is pretty close to ideal results, even at our largest circuits, which have more than 1,000 gates and around 500 RZZ gates. So that was the data loading part, and now we can talk about the full circuit, the full classification, and I'll spend some time on describing the exact setup here so we also understand the meaning of this chart. Basically, what we do here, we take the problem I just mentioned, we train it on simulators, then we take the full circuit that we have, the classifier circuit, and we run inference on the actual quantum hardware. We run inference on 60 test images and report the accuracy of this classification. The y-axis is the accuracy, the F1 score. 1 means perfect classification. And obviously, again, x-axis is the number of 2-qubit gates, and as it grows, the accuracy is going to drop because the effect of noise is going to grow. Here, the red line is the fully noisy result. It's at 50%, as you can expect. The yellow line is actually the 99th percentile of a random guess. Because you only have 60 images, you can expect that even with a random toss coin, you can get better than 50% accuracy in some cases, because you only have, again, 60 images. And that number is around 72 or something. And again, anything above the yellow line means you are getting significant signal in terms of accuracy and your classifier. And we're also super excited to see that all the way to 3,000 2-qubit gates, we are above the yellow line. And this experiment was run on IBM Fez, again, 72 qubits. And in particular, the one very interesting example that we like to showcase is this one dot here that basically shows that even with 2,000 2-qubit gates, you can get 85% accuracy on an image classification task on a quantum computer today. So we run a similar pipeline on Quantinuum again. This time, this is the H2 chip, which has 56 qubits, and it has all-to-all connectivity as our Quantinuum devices, all of them do. And we have some specs here with their 1 qubit and 2 qubit fidelity. And again, we run 3 inferences on Quantinuum device. And we report the ideal results. The blue bars are the ideal simulator results, and the red lines are the results that we get from the quantum hardware. And as you can tell, again, the quantum results mimic very nicely the actual expected results from ideal simulation, all the way for the largest circuits that we run at 664 RZZ gates and around 1,500 gates, total gates. Also, again, here we have very low number of shots. That's one big difference between Quantinuum and IBM, by the way. Because IBM runs are cheaper, you can run a lot of samples and get rid of the variance that comes just from the low number of shots. With Quantinuum, it's a bit trickier. But yeah, even with the low number of shots, with 200 or 300 shots, we get pretty nice results that show that the quantum output is pretty close to the ideal simulator output. Here we are just summarizing the insights that I mentioned. So again, we run these classification circuits on Quantinuum and IBM. So one particular theme one takeaway that I want everyone to kind of have from this talk is that quantum computers are already here, and you can run large-scale experimentations on them. To our knowledge, these experiments were the first ever image classification, real-world image classification done on quantum hardware, and we got pretty good results on par with classical, early-stage classical algorithms. And specifically for Quantinuum H2, we got around 90% signal at 700 2-qubit gates, and for IBM Fez, we got 85% accuracy on our test data with 2,000 2-qubit gates and total 12,000 gates. And we also had detectable signal around 3,000 2-qubit gates, which also agrees with the results that IBM publishes. So the overall experiment is, again, supposed to show that there is a lot of room for experimentation here, and there is enough flexibility in these models to try out all kinds of different solutions. And yeah, this is my last slide. If any of this sounds interesting, please follow our company, BlueQubit. We do a lot of experimentations like this where we run interesting problems on today's quantum hardware, and let us know if you have any ideas of problems that you want to map to quantum. And with that, I'll take some questions.
Questions? All right, I'm coming.
Hi, thank you for the amazing talk.
I have a technical question. Does increasing the number of gates definitely mean an increased accuracy, ideally speaking, if you're running on a simulator?
That's a great question. We had another series of experiments where we were looking at the dependence of accuracy on number of qubits, and we've seen some results like that. This particular series of experiments was geared more towards understanding how big of a circuit we can run on quantum hardware before noise starts killing the results. But in terms of growth of accuracy, we definitely noticed that, but depends a lot on the model and the setting. And then again, once you take that overall solution to quantum hardware, you still need to take into account the noise. But overall, and then there is also the difficulty of training these circuits when you grow the number of qubits. So there is a couple of trade-offs you have to work with. So it's not just a simple yes. But yeah, we've definitely seen some of that in some of our experiments.
And also, do you see the effect of entanglement in the accuracy? Like if the circuit is more entangled or if there's no entanglement present, does that affect the outcome, the accuracy?
Yeah, that one actually is more clear because in the diagram that I had where I had the classification layer, we noticed that definitely the more layers we have, which corresponds to more entanglement as we have deeper circuits, it's basically, it's obvious that deeper circuits give you more flexibility and better classifiers. I should have mentioned that in the slide. Thanks for the question.
Thank you so much.
Hi, just a quick question about your results with IBM. Did you do any study on with using the error mitigation techniques on IBM, or was it sort of just a single circuit?
We definitely use some of the techniques that they already provide in Qiskit. I would say it makes a big difference if you're running just by the default settings or you're using some of their fancy techniques. And what we also noticed is that depends a lot on your use case, and there is a lot of room for improvement there. This is like our kind of stage one of exploration. That's definitely an area we're looking into spending more time on and optimizing the circuits specifically for the runs on IBM so that we have error mitigation there.
Thank you.
So there are lots of ways to use machine learning. Why choose image classification for quantum machine learning?
That's a great question. When we were thinking about different ways that we can build algorithms and run them on quantum hardware, we were thinking about taking something that is traditionally considered like hard, or people don't really approach it because it seems like a really difficult task. And image classification was one because the idea of encoding images into quantum computers just sounds kind of wild. Like it's really hard to approach that kind of problem out of nowhere. And we had a paper on data loading last year. So it was just very natural to try to apply our data loader into images. So we run some experiments and we saw some nice results, and we thought that, okay, now that we can actually encode images into quantum computers with some good approximation, how about we look into downstream applications of that, and images, downstream application, machine learning. First thing you can think of is classification. So that's how we arrived at this problem.
Thank you.